yeah, tonight's presentation, I'm going to be presenting how to do optical character recognition with MXNet Gluon. So this is a project that has been done by a few people in my team. So we've got Jonathan, who's on an internship with our team, who's done the majority of the work, and Thomas has been a mentor. So I can't take credit for any of this work, but it also means if you spot any bugs, then it's not my fault. So what's the problem with optical character recognition? So it's the fact that there's still large quantities of handwritten data out there, handwritten notes that we can't search through, we can't analyze. So this could be a problem, for example, in the medical industry, if doctors are taking lots of notes, it's all done handwritten, and then we need some way of processing that data. So we want to convert this this analog data into digital data by doing a combination of computer vision and then NLP. So it's quite an interesting problem to look at. So to get started on solving the problem, we obviously need our data set. And the source of our data set that we're using in this project is through the IAM handwriting database. So it's a reasonably old data set. It's been around for a while, but it's quite comprehensive for this problem. So here's just a few summary statistics. So there's lots of different writers, all with different varieties of handwriting. And then we've got over 1,000 pages of scanned text. So it's not huge, but it's one of the best data sources out there. And this is for English, and on the right-hand side, we see an example of what that data is structured like. The data, you actually need to register to get hold of it. I provided the link there. You get the username and password. And then the data comes in an XML format. So I'm going to show code as well as part of this presentation. And the project's got its own GitHub repo. So you can find that. Let's switch across. At the following link. So this can be shared afterwards. All the code samples are in here. The very first thing we're going to look at is the data. So this is the website that I was referring to, where you can register and download. And we've got a file that implements the Gluon data set. So if you have worked with Gluon before, you'll have seen the concept of a data set, but if not, data set just is a way to be able to retrieve a single sample. So here is where we're defining a class called a data set, and we only really need to implement one method. It says get sample I. So we provide and we define a method called getItem, which is Python method. So this gives us the ability to index, just like a list. And here there's lots of other helper functions that we've defined, or helper methods we've defined in this class that's going to download the data, parse the XML. This is really going to be bespoke to your problem, but in this case, that's all done. And then this getItem is just going to return the image and then the associated output. So typically, you would define, let's say, the image and a bounding box for certain regions that you're interested in. We'll see examples of that. Or it could be a line, and then it will give you the text that represents that. And so this data set can handle all those different variants that you want to extract from this data set. So now we've had a quick look at the data set, let's move on to certain ways that we could solve this problem. So Jonathan has come up with a pipeline that breaks it down into subtasks, where we're going to start with the whole page, we're going to isolate the handwritten text region, then we're going to identify the lines, and then we're going to go from the lines to the actual text. The first components are going to be more specific to your problem. So in this case, we've got quite a strict structure for our data. But then the last component, which is the handwriting recognition step, is more general. So you can come up with your own object detection to find the handwriting. Depends what data you're working with. But the last part is more generalizable. So first part that I mentioned was page segmentation. So that's where you've got your input image. You want to identify a bounding box of handwritten text. So there's only one region of handwritten text in these examples, so we're only detecting one object. And the traditional way of solving this was using a protocol called MSURS. We'll look at that and then move on quickly to how to solve it with CNNs. So MSURS don't know too many of the details behind the algorithm, apart from the fact that the output is blobs and blocks that will denote words. So on the left-hand side, you'll see all the regions that it's identified as blobs. And then we have some heuristic algorithm that's going to combine these blobs to give bigger blocks. And the way we do that is just expand each block by a certain amount, and if we have some overlap, then we're going to combine them. So that's done iteratively, and we have these hyperparameters that control how much we want to increase the box. So lots of fiddling about, very sensitive to the hyperparameters that you're going to use. So a preferable method for solving this is through CNNs. So this is what a typical architecture would look like for solving this problem with convolutional neural networks. So we're taking the input on the left-hand side, which is just the raw pixel values. This is a grayscale image for all these examples. And then we apply convolutional filters. So this is a 3x3 convolution to start with across the whole image, and 16 of those filters to give us 16 channels, followed by a batch norm. And then this is pretty typical for a convolutional layer. Repeat it a few more times, have a few max pooling layers to reduce the dimensionality. And then the final part is where we take the feature map and we apply a few dense layers. So they're fully connected layers that are going to give us 4 outputs. And this is predicting the bounding box for the handwritten text region. And the 4 parts, so the first 2 components are predicting the top left corner of the bounding box. You'll see a very small dot on the right-hand side, or the top left corner. And then we've got the width and the height that's also being predicted, which is going to give us the width and the height from that point. And that will define a bounding box. We've obviously got in this data set, the labels for this bounding box. So we can do optimization to refine the box and improve all the weights. Lost connection for some reason. Well, the next part I can talk about is pretty simple, but to avoid any overfitting in this network, it's pretty common to do data augmentation. So Jonathan's done some data augmentation that shifts and translates and scales some of these input images. Would have shown you an example. Then once we've done that, we do the whole training, which, because we've got the labels, we can calculate the loss and then backpropagate the loss. To begin with, the loss was mean square error on all those coordinates. Jonathan actually found that by optimizing intersection over union, which is another method for calculating the loss, that was give better results than mean squared error if you're just looking visually. And he actually started off training the network with mean square error, and then switched his loss to intersection over union. Because if you started with intersection over union, by random chance, often you get 2 blocks, the truth and the prediction wouldn't intersect at all. And so there's no way to actually improve, because your loss you have no gradient there. So that's why he started with mean square error and then switched to intersection over union. And so that's just a diagram of how intersection over union is calculated. You've got the 2 boxes, one is your prediction, one is your true area, and you get the intersection between those 2, and you divide by the union of those 2. So clearly, the 2 boxes align very closely. The top part of the fraction is going to be higher, and the bottom part of the fraction gets reduced, so you're going to get a bigger number overall. Intersection over union improves, and that's what you want. You've got the 2 boxes to align. And since this
Did your dataset get these bounding boxes like as true values from the beginning? So these
yes.
are unlabeled.
Can you
Yeah.
repeat the question?
So the question is, did the dataset originally have the bounding boxes? So the dataset has bounding boxes of lots of different things. It's got the bounding box of the handwritten text region, which is what we're trying to do now. Also has the bounding boxes of each line, and it also has the bounding boxes of each word. So we're just using the first part of that, and then later we use the other bounding boxes. But there's truth for us to learn from, and that's what we're trying to fit.
But why do you need this?
So this is if we want to apply this model to similar data to this. that doesn't have those bounding boxes, so we want to learn a model that will be able to isolate a handwritten text region. But we could, yeah, if you were just interested in being able to go from a line to handwritten text that's already been cropped already, then we wouldn't need this part of the model. But this is just so we can go end to end from a page down to the text. This is just the first part.
But again, the goal is what? If you have a real scene image, like with printed text,
Yeah.
and written text, then what would happen?
So if you gave it a similar image, it's got to be a model that's got to be applied to a similar domain which it was trained.
Right. So it should be pretty clean scene, clean picture with printed text on the top and written on the bottom.
So with the data augmentation, it shifts it in such a way that there doesn't always have to be the printed part in the image. This model would need to be applied to a white page with some handwritten text on in a block. But that's just this part of the model. Later, we'll get to more low-level models that can be applied to more wide-ranging things. So we're moving on now to the line segmentation. So once we've identified the area of the handwritten text, we're going to predict the bounding boxes for each line we can identify. So this problem has multiple objects to detect. We use slightly more advanced methods to do it. So Jonathan opted for using SSD, which is Single Shot Multibox Detector for object detection. I'll show you the architecture for that. But again, we do data augmentation. In this case, data augmentation was applied slightly differently. So we've essentially dropped out some lines at random and just painted them out and removed the label for them. This is to stop the network remembering certain positions of lines relative to each other and always predicting a certain amount of lines to add that variability. The dropout ratio that was set for this was 15%, a 15% chance of each line being dropped out. Are most people familiar with SSD? Well, show of hands. Has anyone come across SSD? Okay, not many people. So SSD is for detecting objects, and the way that it's done is we start with some prior, what's called anchor boxes, and these boxes are deterministically generated. There's an algorithm to generate them, and they're placed throughout the image. Then your neural network is applied to refine these boxes. So instead of predicting where the objects are, you predict the change that needs to be made to the boxes to isolate an image. And because these boxes cover the whole image, the chances are there's going to be an anchor box reasonably close to a certain image, a certain object you're interested in, and you're going to be able to move that anchor box just a little bit to contain your object that you're interested in. So you need to start with prior anchor boxes that are shaped like the objects that you're interested in finding. Typically, this on the left-hand side, this is what a few of your anchor boxes would look like for a given position in your image. This is just taking the middle point, and these are the anchor boxes that you generate. That's fine for most images, but if you're looking at the ImageNet dataset, like a cat kind of could be one of these shapes and a dog. But for the lines that we're trying to detect, we know they're going to be longer than they are tall, or wider than they are tall, so we can build that in as part of a prior of what our objects look like. And the way that we generate these prior bounding boxes, or anchor boxes, is through this function that's in the contract package called multi-box prior, and that you define different ratios that you want to generate these boxes for. So this, going back for why we're working with anchor boxes, on the top right is actually a visualization of all the different anchor boxes that get generated for a given image. So the main point from that is they're everywhere. There's loads of boxes. I think in this example, there were 17,000 anchor boxes. And for every single anchor box, we're going to predict the change that needs to be made to surround an object. Another feature of SSD is that it operates at multiple scales. So we've got different feature maps scaled to different amounts, and within each feature map, it's going to predict objects of a certain scale. So if we're looking at the 4x4 feature map that gets generated after a certain amount of filters and layers in the convolutional network, well, that's going to be useful for predicting bigger objects, in this case, like the dog. But then we could use another feature map to use to predict smaller objects. So here, we're using the 8x8 feature map to do a bounding box for the cat. So that's SSD is useful for detecting objects at lots of different scales. We're not really using that feature of SSD, but it's another key reason why SSD is one of the most popular object detection algorithms. This is what the architecture for SSD looks like. So we're taking the input image again. We actually use a pre-trained ResNet model. So because we're dealing with just about 1,000 or 1,500 images versus ImageNet where we've got 1 million pictures, it's better to use some of those pre-trained weights from ImageNet and use those for our model because they're good at extracting certain features and use the weights that we've learned in that network. So we apply that to the input image, and then for every feature map, SSD network predicts two things. So firstly, we'll see here is for a given feature map, which are the orange parts, we're going to predict the bounding box adjustments. So this is for every anchor box, we're going to work out how much things need to change. And then the other thing we're trying to predict is whether each box actually contains anything. Is there an object in there? And what is the object? So what's the class? And how confident are we that there's something in that box? And we see that it's downsampled lots of times. That's for the multi-scale part. Now, after we've done SSD, it's going to give us lots of bounding boxes. We can do a threshold. We can say, I'm only interested in boxes that we're 90% confident contain an image. But even if we do that, for bounding, because we had so many bounding boxes, in certain areas there's going to be quite a few bounding boxes that we're confident there's an object in. The object in our case is the lines, and we can see if we don't do anything, we just threshold, there's lots of different boxes around certain lines. And there's a technique called NonMaximal Suppression that's typically used. Again, there's an MXNet function that will help us do that. The key idea really is to take the most confident box to begin with. So maybe one of those we're 99% sure contains an object. And then once we have that maximum value, we delete all the other boxes that overlap with that one that we're not quite as confident in. So they're non-maximal boxes, and we suppress them because we delete them. And we apply this process over and over again, and that will remove the clash of many, many different boxes, and we just take the most confident box. So after we applied that technique, you get something more like on the right-hand side, more clean. You've got single predictions for certain lines. This is another example of training. So we're using MX Board here. MX Board is for saving MXNet data and images in a format that's used by TensorBoard. And TensorBoard is great for visualizing. So this is good for visualizing images, predictions, also good for visualizing the training loss over time. And then from this model, we can evaluate the training accuracy and then the test accuracy. Obviously, we're interested in a holdout test set. Actually, it's quite important to note for this problem, the test set is of separate authors. So they've got their own styles of handwriting that we haven't seen in the training set. So that's how the separation is done between the training and the test set. These are just two examples of special cases. So actually we found one case where our prediction was better than the labeled data. So the labeled data is the thick continuous line, and the dotted line is our bounding box. So the training data contained some fold in the paper that was detected as a bounding box, when actually the handwritten text was in a reduced area. But there are some failure cases as well. So if we look at this example on the right-hand side, further down, we've got a prediction that's actually between lines. So it hasn't isolated the handwritten text, so it's not perfect. And there's actually an improvement that Jonathan found. Rather than trying to predict the lines, because that was provided in the data set, we had that truth to predict. He found it was better to predict the words, because that's another data set we had. So we're predicting the bounding boxes for each word, and then combine everything together to give us the lines, because then we can continuously sweep through a line, and we get more context if we have that, rather than just looking at individual words. Okay, so now we're on to the fun bit, the handwriting recognition part. So where are we now? We've managed to get down from a huge piece of paper to the handwritten text segment, and now we've got an individual line. So we're going to work from the line, ultimately, so this is an image still, to the string output that represents what's actually being written in that image. And it's a two-step approach. So the first part is we're going to do the handwriting detection, which is going to convert from the image down to a matrix that gives us the probability of each letter in the alphabet across every point in time. So we're going to sweep through this input image, and we're going to work out which letter is at each part. And so that's embedded in the model. So this is a model that we could use to do that. The first part is we use a convolutional neural network again. So convolutional neural network has a filter that's being applied across the whole image. After we do that, we get image features. So it's not the raw pixel values, but it could be some features like certain edges, certain curves that are being picked up by these filters. So that's the embedding of our input image. And then based on that, the image features, we take slices from this feature map, one at a time. So here, for time 0, we're taking the feature map, first feature map slice that came from the first part of the image, and we're going to pass that into an RNN, well in this case it's an LSTM, and we're going to take a slice at a time from our image feature map, and we're going to sequentially work through that with the LSTM. So the LSTM is going to be able to pick up on more of the context about what we've seen before. So if we start to see, maybe if it's a C or something like a curve, then we're more likely in the next step to predict a C again, because we're seeing that continuation. So the LSTM is getting the context and be able to make those temporal predictions, while the CNN is picking up more on the individual image features, so certain edges. And then the output at each sequential step from the LSTM is a prediction, or gives us the probabilities of all possible characters. But what we've shown in this diagram is just the argmax essentially. So the letter with the highest probability. This is all made up data, but this is in theory what our model is going to give. This is called the CNN-BiLSTM. So one point that hasn't been represented in the diagram is this is a bidirectional LSTM. So in addition to working through the data in one direction as you read, it also works in the other direction, starts from the back and works to the front. And it combines those two together. So you have context from both ways. An extra improvement that was added, so this is taking inspiration from what was used with SSD, looking at multiple scales and resolutions, was to do what we just said. We're going to work with an LSTM applied to the CNN features, but then we apply an extra downsampling layer. So just going to scale the image down, and then we're going to apply another LSTM. So this helps the model deal with different types of handwriting. Some handwriting is very big, and some handwriting is very small. Then we've got two different models to handle those two cases. And at each time step from these two LSTMs, we combine their predictions, and then we run them through a fully connected layer to make these probability predictions. For every character, we want a probability at every time step. That's the matrix that we generate from these models. But we're still not quite there. We're close. We've got these probabilities. But how do we work from the probabilities back down to a string? So this is a bit of a problem. We can solve it in different ways. The most obvious way is that we collect labeled data for every single slice, and we label what letter that denotes. So we could collect some data that's going to take maybe a pixel slice at a time and say this is letter H, 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 E, E, E. But that's going to take a lot of time to collect that data. We're not going to be able to label much data at that rate. Much easier if we just have an image and we then have the string representation. So there's a solution called CTC Loss, which is called Connectionist Temporal Classification Loss. So this theory defines a collapsing function, and it lets you work from two different length sequences. So we've got an input sequence here, where we've got lots of repeated characters, lots of H's followed by lots of E's, and it squashes everything down into a continuous or a smaller output sequence. The good thing about this is that it's differentiable. So once we go down, we can evaluate the loss and pass the gradient back out again. And it's got a few extra features that are byproducts of that procedure, is the fact that it's monotonic. So we're going to be working through time from left to right, and that we've got a many-to-one relationship. So we could get many parts of the input sequence that represent a single point in the output sequence. So here we've got lots of H's, many H's, but they all get squashed down to a single H. And it doesn't work in the opposite way. And this is required for the gradient to propagate back. That was a bit of a simplification, that last diagram. So running through what's actually going on under the hood. So we're taking our input image again. We're running it through the CNN, the RNN. The RNN is spitting out probabilities for each character. Now in this simplified example, we've only got 5 characters. Well, we've got 4 true characters, and we have one special character, which is called the blank character. The blank character is used to separate words. It's different from a space. A space is its own character. But in the previous slide when we saw the compression, we have a problem if in hello we have 2 L's, because they're all going to be squashed down to 1 hello. But if letters are separated by this blank character, when we do the compression, we'll have 2 L's. So that's what that blank character is used for. And so when we're predicting the probabilities for each character, we have to also predict for the blank character too. So our model, our RNN, spits out these probabilities for every time step. And then we need some way of reducing these probabilities down. So we can have multiple different paths through this probability space. So let's start with a simple case. We're just going to take the most probable character from each time step. So if we work through, we've got the H as the most probable to begin with, then E, and then the blank space, and this is what we're finding across the first row. But there's many other ways. They don't have as much probability, but we could, for example, have gone from H to H to E to L. There's loads of different combinations. So this is getting reasonably intractable if we have to search through all the combinations. But luckily with C2C, we can take advantage of dynamic programming to cache some of the results. And we can do this because we had that monotonic rule that's always working forwards and doesn't work backwards. So that actually gives us shortcuts to calculating what we want. And now, once we've compressed all the different paths through this space of sequences and characters, we can get ultimately a probability for each output sequence. So given the character and probability matrix at the top, we can say, okay, there's a 70% chance in this case that it's the word hello, and a 10% chance that it's hello. And we get this probability map based on doing these calculations. We know the truth of this, because it's labeled data, is 100%, and so now we have something that we can calculate the loss on. And this is differentiable, this process, because we were just timesing numbers and we're adding numbers. We can always backpropagate through that. And based on this loss, then we can go all the way back through the RNN and the CNN, update all the weights to give us a better prediction for the next pass, which is backpropagation. And so this has allowed us to take a prediction from the model with many time steps to a label with less time steps. It's doing that alignment problem. Okay, in this case, so the simplest way, that was all for training. When it comes to inference, our model is still predicting the same thing. It's predicting this top matrix, where we've got the characters and the probabilities for those characters at every time step. The one example that I gave, where we take the maximum at every time step, here it was H, E, blank, LL. Well, that's one way we could do it, and that's just called the best path method, taking the argmax. So this really, really reduced problem, we've got 3 characters. We've only got character A, B, and the blank character. And then we're looking across 2 time steps. So we've got time 0 and time 1. And the associated probabilities for each of those combinations. So the best path, if we look at time step 0, is to do the blank character. And then the next time step is also to take the blank character. So the best path through this matrix is to go blank, blank. Blank and blank get compressed to nothing. So the best path here is blank, if we use that. But actually, there's a few other paths that we can take through the model. So if we, for example, looked at working out the probability of A. So there's a few different paths to get A. We can, to begin with, go for a blank and then move to A. That's going to get compressed to A. But we can also go from A to blank, and that's going to be compressed to A. And we can also have A and an A, which gets compressed to A. So there's 3 different routes to get to A, but there was only 1 route to get to blank. And if you actually add up the probabilities, we can get a higher probability for N. So A was a better prediction than blank, even though if you just went through and took the maximum at each step, you'd end up with kind of the wrong answer if you want to go for A. But this is not something that you can do for all combinations, because in this case, the amount of paths you're going to have to evaluate are the alphabet length to the power of sequence length. So for a typical case where you're predicting across 81 characters, so capitalizations and numbers and punctuation, you could have about 81 characters. And then this is the power of 30, there might be 30 time steps you have to go across. That's going to be a lot of paths, you can't really do that. So the way this is done, or the way we approach this, is through beam search. So we can start off with our blank character and then evaluate a candidate set. So we could fix our K to 30 characters, for example. And we're going to take the most likely 30 characters. And then from there, we evaluate the probability of that character and the next character. And so we keep a record of the best so far, the best 20 predictions so far. And we work through, and we're always keeping a candidate set of just 20. So this example in the diagram is of 3 time steps. And by the time we get to the 3rd time step, we can see the best combinations that we've got. The candidates were empty and A and empty, and A and B. But this beam search needs to be tweaked if we're using C2C, because the problem we mentioned before, there's many different paths that evaluate to the same string at the end. So there's a modified C2C beam search where you combine the probabilities across routes. So in this case, let's say that we started with the empty string. We evaluated, this is a beam with a width of 3. We've got 3 different proposals. And then for the next time step, we are searching across, so we go from the empty string again to A. Well, the probability of having a reduced string of A has got a few different routes. We could have gone empty A, we could have gone A empty, and we could have gone AA. So it combines those three probabilities together. So that's a modification of beam search. And actually, Jonathan used a slightly different library to do this component, but CTC Loss is implemented in MXNet. It's just for the inference part that we used a slightly different function. So now we've got a way of being able to find a list of candidate strings. So we had our image, we've gone through this C2C process, and now we've got 20 different candidate strings based on our beam search. The extra parts that Jonathan has added on, firstly is he's added Lexicon search. It's essentially just spell checking all of the proposal strings. We've got 20 suggestions, and to begin with, for each string, tokenizes and then runs every token through a spell checker and looks at the edit distance of the spell checker's suggestions, and if he picks the suggestion with the minimum edit distance. So if it's not too much of a change, but it's a real word, then it's going to be replaced. This is just making sure that the predicted words are actually words. And running it through a spell checker is quite an effective way of doing it. And edit distance, just to recall, is if you make a switch of a letter, or if you add a letter or delete a letter, you're going to have to be penalized with 1, and it's just an accumulation of that count, how many edits you've made to the string. And lastly, this is using Gluon NLP. So Jonathan's added a language model on top of it. So we've still got those 20 proposals from the beam search. We've spell checked them all, so they're all containing real words. But then using the language model, we can get a prediction for how likely that sentence is. Using the language model that returns probabilities of each word, given the previous words in the sentence, we can get a probability for each one of those candidates and say, out of all of them, this is the most likely to be the real sentence. This is how he was using Gluon NLP. So you can get a language model using Gluon NLP model get model. You initialize the input state, because this is a recurrent network. You have to initialize it with something using the begin state method. Then tokenizing his string, which was the proposal string. Checking if it's in the vocab and retrieving the ID, and then passing it to the language model to get predictions for the next step. And using this language model, you can calculate the perplexity. That's a metric that's used. And you evaluate the perplexity for every string and pick the candidate with the lowest perplexity. If you've got a lower perplexity, it's more likely, given that language model. And lastly, these are some results. So of all those different approaches, so we were building up the model, but if you just started with the greedy output, which was taking a maximum, the most likely character each time step and compressing, you get the suggestions on the left, and then adding the lexicon search, the spell checker, and then the beam search, lexicon search, and language model gives the best prediction. So if we look at the top one, to begin with, it's got these tuppy things, and then by the time we get across the beam search, it's corrected that to get these lovely things. So there's still a few mistakes, still working on improving the model, but adding those extra things improves the model.
I guess that different lines are independent, right? So you don't use the main language model between lines.
Yeah, it could be, but it's not used in that way in this case. Yeah. All right. Thanks.
So for inference, so you said you use beam search, but I'm wondering, can you use some kind of a dynamic programming approach similar to that Markov model? Because for training, you use dynamic programming.
Yes, the dynamic programming part was purely focused on calculating the CTC loss. it was making use of that compression function. And the way that compression function is defined, it gives you those shortcuts that we can use dynamic programming.
Oh, so that is not applicable for
And it is still used in inference, the dynamic programming part, is if we look at the beam search again. At every point that we want to evaluate the probability of having the sequence, so here, we've got the probability, for example, of there being an A and an T. The calculation of that probability uses the dynamic programming optimization, because to get to this point, you have to do the compression. So, for that part at least, it's being used.
Oh, so it's just for compressing.
Yeah, the C2C or connections temporal classification in the paper where this was used first, they define this compressing function. And there's the dynamic programming shortcuts to compute that function, or to compute the probability of a resultant string using that compression function.
Thank you.
It's okay.
Do you use any named entity recognition to avoid looking up words that won't be in your dictionary at the final stage?
Hasn't been applied in this case,
Oh.
but yeah, it's a good idea, for sure. Right.
So maybe it's a dumb question, but for obviously connecting, measuring the maximum likelihood estimation of what the string is going to get these weird, not useful, empty string kind of things. Then a programming approach seems to be much more fancy. Something simpler, and I wonder what the problem is with it, is just doing like give sampling and just kind of sampling through, walking your way and counting up stuff and just stopping after a while. Does that not work for some reason?
So with CTC loss, I'm not sure with sampling you'd be able to back propagate the error. For inference, that would work, I'm pretty sure, if you had lots of samples and you collated it. But for the training part, there is a way to go backwards, and then you can update all your weights of the RNN and the CNN.
Thanks.
Yeah.
I'm kind of curious about the application of the language model. So given the dependence between, or the interdependence between the different words in the sentence, how, let's say, what order the language model are you using in order to decide, let's say, the most likely word for each one? And are you looking also like forward context and backwards as well?
I think to work out the complexity of the given candidate. So I'm not too sure on the details of this specific language model, but I'm pretty sure it will be applied in sequence. Go ahead.
This one is actually the train on witness too. And this AWD is one of the state of art control. And it's actually applying the weight drop on the weight matrix between the RCN layers. So you have weight between the weight connections of the two layers. The random drop on the so you would like to handle these
It was more like the question whether, like, okay, if you were deciding the middle word in the sentence, are you looking at, let's say, what are the probabilities of all the other words? Like, how big does the language model have to look in order to make a decision? Or are you just going forward?
I think this is just going forward to work out the complexity in this
This
case.
is a unique direction.
Yeah.
So you're using standard data sets like the public data. So it means that there should be some kind of baseline matrix or everything. So, and it means that this kind of problem, like the basic algorithm should be some hybrid approach, development with HMM. So can you compare CTC with this? Because CTC should work fine with a lot of training data,
Yeah.
but look at your data, it looks like it's not a big amount of data. So I'm just curious, like, did you compare it with baseline? If it's any.
So Jonathan didn't come up with this particular model, and so the CNN-BiLSTM. But in the paper, they've done a thorough investigation, compared it with baseline models, which was HMM, and I don't think they used HMM with, maybe it was with CTC loss as well. I'm pretty sure they did that comparison in the paper, and this was giving better results. And they did it on 2 different data sets. So it was IAM as well. I think there's some French handwriting data set as well. I think on both cases, this gave better results than the old model. But yeah, you're right. So for C2C that I talked through, that's not tied to neural networks. It's just any model that returns this probability of characters over time matrix, you can work with that and compress it with C2C. So it's pretty independent. It's not to do with neural networks. Yeah.
And I guess this model was trained on English alone, right?
Yeah.
So given that, how much of the pipeline do you think can be reused if you want to do transfer learning for another language?
So yeah, you need a different language model. You need the different lexical search. The RNN, the CNN part, I would expect the features that would learn, the different edges, to be pretty reusable. The LSTM is pretty specific. The way it's applied here, bidirectional, which the slices are taken from like vertical slices. So if you've got Japanese, for example, that you might read from top to bottom, then you need to change the model for that as well. So you're expecting it to work for languages that can be read horizontally. Some of the features learned in the LSTM I'd expect to be reusable as well. When you start to see some like combination of edges followed by other edges, that would be part of it as well. So some parts, not some other parts. Yeah.
So does this approach to the OCR component as well as statistical approaches that doesn't use dependence?
This is currently the state of the art for handwriting recognition, as I understand, using similar models to this, based on the evaluation on those 2 different classical databases. Yeah.
Do you have a live demo?
A live demo. I've got more code. I can show you, if everyone's got time and is interested, I can show you the code for one of these models. Oh, a live demo. Oh,
Maybe you should
no,
write it. You can write something for it.
I'll tell you what you've written. Yeah.
You framed it over here, right?
Yeah. It's all trained up here. Yeah.
Do you have cases where people have like scrubbed out the word and then rewritten the same word later? Do you know to like, if they put a line through it, then they're probably meant to delete that and kind of remove that from the model? Or?
I'm not sure whether that's recorded in the labeled data set. But I did notice an example in one of these cases where someone had scribbled something out and it did detect it as a character. So it assumed that whatever this learned, it had not learned that. But potentially you could do it if it's labeled as well. Alright, thanks everyone.
Thank you.